I'm going to talk today about the finite dimensional representations of the Lie algebra SL2. So I've set up representation theory for Lie algebras. So today always G is going to be the Lie algebra SL2 of C, and I've given you the definition of what a G module means. In fact, we saw that it's exactly the same thing as a left module over the universal enveloping algebra. And when I use rep, I'm talking just about finite dimensional representations of this Lie algebra. Okay, so that's what we're going to do. We're going to totally understand this category of finite dimensional SL2 modules. So let's see, we need to actually make some calculations today. So we haven't done so many of those. So we're going to use the basis that I've given you before for this Lie algebra: E, H, and F. And remember the commutators that they satisfied. The commutator of E and F was H. The commutator of H and E was 2E. And the commutator of H and F is minus 2F. So the observation that so much of this rests upon is the following. If V is a vector, let's maybe make it a non-zero vector, in some G module, V such that HV is lambda V, so lambda here could be any complex number, then EV and FV satisfy the following. H on EV is lambda plus 2 EV, and H on FV is lambda minus 2 FV. So because this is just the equation to say that V is an eigenvector for H of eigenvalue lambda. So usually in this subject you don't use the words eigenvector and eigenvalue, you say that V is a weight vector of weight lambda. So that's just a little bit shorter to say. Okay, so it's always about H. We always use this diagonal matrix in there for our linear operators that we're going to take eigenvectors and eigenvalues for. So what I'm saying is that if you start with a weight vector of weight lambda and you apply E to it, you get a new weight vector of weight lambda plus 2. And if you apply F, you get a new weight vector of weight lambda minus 2. So E and F, they add 2 or subtract 2 from weights. And of course, that's just a straightforward consequence of these two commutator relations, the 2E and the negative 2F in there. But it's so super important. Let's prove this. Let's at least prove it for the E case. So by definition of module, HE acts on V as H of E of V minus E of H of V. And HE is 2E. And HV we're assuming is lambda V. And then you just rearrange that and you get what we want. That this, so I bring the lambda E over the other side, I get lambda plus 2 EV, and there it is. Okay, so that's and for F, of course, it's very similar. Very simple observation. E raises weight by 2, F lowers weight by 2. So if you have any G module, finite dimensional, in general, in a G module, there's no reason why you should be able to find an eigenvector for H, right? Because if it's infinite dimensional, it needn't have any eigenvectors at all. But if it's finite dimensional, you can always do that. We're working over an algebraically closed field. That's crucial here. You can always find a non-zero weight vector because our field is algebraically closed, right? The characteristic polynomial of the endomorphism of V defined by the action of H will always have a root in your field, and hence you can always find an eigenvector for some eigenvalue of weight, some complex number. And then the idea is you take your V. It might be that EV is 0, but if it's not, then there's a new non-zero vector. V is of eigenvalue of weight lambda. EV is of weight lambda plus 2. You can keep going. You can apply E again. Might be that that's 0, but if it's not, then here's a new vector of weight lambda plus 4, and so on. You can't go forever, because eigenvectors of different eigenvalues are linearly independent, and our V is finite dimensional. So eventually you get to the point you get to a weight vector that is killed by E. And that's a technical definition. Such a vector is called a highest weight vector. So it's a vector V in V, so that HV is lambda V for some weight lambda, and EV is 0. Okay, so in any finite dimensional representation, any non-zero finite dimensional representation, such vectors exist. And what we're going to do is we're going to show that any finite dimensional irreducible representation is determined uniquely up to isomorphism by what's called its highest weight. And that's just the weight of a highest weight vector. And this weight is always going to be, actually I'm going to use n, it's always going to be a natural number. And so what we'll do is we'll write L of n for this unique, irreducible, finite dimensional representation of highest weight n. And in this way, we'll see that the natural numbers actually parameterize the isomorphism classes of finite dimensional irreducible SL2 modules. So this will give this very elegant and simple classification. They're just indexed by natural numbers. In fact, the dimension of L of n will just be n plus 1. So let's just really quickly just look at a few examples before we try and prove that in general. So where should we start? I guess we should start with the trivial module. Remember, any Lie algebra has a trivial representation. It's just one-dimensional with all elements of the Lie algebra acting as 0. So this is of highest weight 0, there's only one line's worth of non-zero vectors in here, and h acts as 0, so that's the highest weight. So that's going to be the L of 0, labeled by the natural number 0 in this classification. And the next, there's going to be the natural representation, the defining representation of SL2. It is 2 by 2 matrices by definition, so it acts on column vectors, which has that basis V1 and V2. And if you remember that H is just this matrix, so that means that the way H acts on the first standard basis vector is just as 1. So this is weight 1. And the way that H acts on the second standard basis vector is just as -1, so that's weight -1. And in fact, you can easily see everything from our matrices, right? So F will send V1 to V2, subtracting 2 from the weight. E will send V2 to V1, adding 2 to the weight. V1 will be the highest weight. So that's going to be the L of 1. Yeah, it's a two-dimensional irreducible representation. And then I guess in general you can look at S to the NV, the nth symmetric power of the defining representation. So that's going to be L of n of dimension, nth symmetric power of a two-dimensional vector space is of dimension n plus 1. So let me see. This is going to have basis of monomials in the basis of the defining representation. So V1 to the n, V1 to the n minus 1 V2, V1 to the n minus 2 V2 squared, and so on all the way down to V1, V2 to the n minus 1, and V2 to the n. And so the weights of these things, this is of weight, it's n times V1, so it's going to have a weight n, because V1 had weight 1. And then this is going to be n minus 2, n minus 4, 2 minus n, and minus n. And the e's and the f's, they just, so it's just like a chain. F subtracts 2, e adds 2, so they move you down and up this chain. So I guess actually if you're acting on V1 to the n, f is going to give you n lots of this next vector down, because it'll change any one of those n v1s to a v2. So I guess if I want to just go down, I need to put 1 over n f, and then 1 over n minus 1 f, and 1 over n minus 2 f. They'll move you basis to basis. And this would be E, or this would be E changes a v2 to a v1. There's two choices, so that's going to be a half E, that's going to be a third E, and you see the pattern. How this goes. I guess we should just prove that this is irreducible. It's certainly a representation. And on this week's homework, there's a question about symmetric power. So if that's confusing you, you'll see that on the homework. It's a quotient of the nth tensor power, and the Lie algebra acts on that tensor power because of this co-multiplication. And the nth symmetric power is actually a G-module quotient of the nth tensor power. And to see that it's irreducible, well, you see, we've got all these weight vectors, this basis of weight vectors. All the actual weight spaces, eigenspaces, are all one-dimensional. So if you had a non-zero proper submodule, you could pick an eigenvector, pick a weight vector in that, because this H is acting diagonalizably. Look, all the eigenspaces are all one-dimensional. So on any G submodule, that's going to be stable under the action of H, so it's going to be diagonalizable on that submodule, and you just pick a weight vector. That gives you a multiple of one of these monomials in this basis. And then once you've got one of the basis vectors, well, you can just act with E and F to pull you up or push you down the chain. Any one basis vector generates all the other ones if you're allowed to hit it with E's and F's. So take any weight vector, and that generates. So it's kind of very cheap and easy argument. You can fill in the details. Okay, so let's see if we can prove this classification in general. So there's one lemma, though I said we were going to actually have to calculate, and here's the calculation. It's really not that bad. If little v in V is any vector in any G module with E V equal to 0, so any vector killed by E, the lemma tells you how to calculate E on f to the n plus 1 V. And it says it's n plus 1 f to the n h minus n V. This is for any natural number n. And so here's the calculation. So this is maybe the first place where you see how handy it is to have the universal enveloping algebra around. I mean, this made sense for the Lie algebra acting on the vector v, but it's even better to think of this guy here, E f to the n plus 1, as being a monomial in the universal enveloping algebra. There's no Lie brackets there, that's just an associative algebra monomial. And V is just a module over that associative algebra. So that's very convenient in this notation. And so the proof is just, well, E f to the n plus 1 V, that's the same as taking the commutator in the universal enveloping algebra, E f to the n plus 1, and acting on V. That's because E kills V. So let me just write that, emphasize that this right here, this is the commutator written in the universal enveloping algebra. Okay, but so now we're taking a commutator of something in an associative algebra, so taking commutator satisfies the Leibniz rule, so we can calculate that. It's just so we have to differentiate each of the f's, so it's the sum from 0 to n, f to the I, E f, f to the n minus I, V. EF is H, and now I'm just going to use that HF is F H minus 2 in the universal enveloping algebra. That's our Lie bracket. HF is negative 2F, but it's more convenient written that way in the universal enveloping algebra, so I can pull that H to the right. So they commute, and each time it goes past 1, you subtract 2, so it's going to be H minus 2n plus 2iv. And then you just have to do a little bit of algebra, add up those coefficients to see that you get n plus 1, H minus n, v. And that's the proof, right? So that's the calculation. It's not really that bad. Corollary, if V is a vector killed by E, so the corollary tells you how to calculate E to the n plus 1, F to the n plus 1, V. Okay, so this just follows very easily by the lemma, which tells you how to do E on an F to the n plus 1, V, and now I'm just doing loads of E's on that. So this is just, well, maybe I'll write out the proof. So this is going to be equal to n plus 1 factorial h minus 1 h minus n v. So the one-line proof, you just calculate it. It's e to the n, e f to the n plus 1 v, and then you use the lemma. That's e to the n plus 1 maybe I should put the e to the n here, f to the n h minus n v, and then this is just a new vector which is killed by e, and you induct on n. To get the corollary. Okay, so those are our calculations. I think they're totally not too bad to do. Okay, so now towards the classification of finite dimensional representations of SL2. So I'm going to take, let me get rid of that. I'm going to take some complex number lambda. I'm going to let B be the subalgebra of G, or SL2, just spanned by H and E. So it's upper triangular matrices of trace 0 in there. This is actually a solvable subalgebra. And it maps onto the span of H. E in here spans an ideal of B, and if you quotient out that ideal, you just get left with the diagonal part. And then I'm going to let C lambda be the one-dimensional irreducible B module on which H acts as the scalar lambda and E acts as 0. Okay, so this is just taking the one-dimensional module for this trivial one-dimensional Lie algebra on which H acts as lambda, and I'm just viewing that as a module over this upper triangular subalgebra B by just inflating it through this surjective Lie algebra homomorphism. B, by the way, the reason it's called B stands for Borel. It's the Borel subalgebra in there. As B is a subalgebra of G, the universal enveloping algebra of B is a subalgebra, a unital subalgebra of the universal enveloping algebra of G. And then I'm going to form what's called the Verma module, M of lambda. And so this is taking this one-dimensional representation of the Borel, and it's inducing it to G. Inducing means tensoring up over U of B with U of G. So this is the Verma module. So that's a G module now. So let's see if we can understand this thing. As U of G has basis f to the I, h to the j, e to the k, I, j, and k greater or equal to 0 by the PBW theorem, and those guys are a basis for the universal enveloping algebra of B sitting inside, you see that U of G is free as a right U of B module with basis just these f to the i's. Right, so we're tensoring over the big algebra over a subalgebra, and usually you can't understand that, but you can if this is a free module as a right module over the subalgebra that you're inducing over. And in that case, this tensor product, you can just think of it as, well, let me just write it. It follows that M of lambda just has basis as a vector space just by applying this, these basis elements for U of G as a free right U of B module to a basis for the module we were inducing, but that was one-dimensional. I'm going to denote these by f to the iv plus. Okay, so instead of, so this was the 1 in that one-dimensional module I was inducing, and I'm going to denote that linear basis for the Verma module. I'm going to denote those by f to the I v plus. Note also that f to the I v plus is a weight vector. So what's its weight? Well, v plus would be just 1 tensor 1 here, right? 1 tensor 1. And the way h acts in the same way that it acts on c lambda, and on c lambda it acts as lambda. So the vector v plus itself, f to the 0 v plus, that's of weight lambda. And then remember, each time you apply f, you subtract 2 from the weight. So this has weight lambda minus 2i. So theorem 1. If lambda is a complex number, but not a natural number, m of lambda, the Verma module, is an irreducible G module. And if lambda is a natural number, well then m of n has a unique submodule isomorphic to m of minus n minus 2, and since it has a unique irreducible submodule, it has a unique quotient denoted L of n. So that's this Verma module m of n over m of minus n minus 2. And this is a finite-dimensional irreducible representation of highest weight n and dimension n plus 1. And finally, every finite-dimensional irreducible representation of this Lie algebra is isomorphic to L of n for a unique natural number n. So this is the classification of finite-dimensional irreducible representations of SL2. So this proof is kind of very interesting, and it's sort of quite easy because SL2 is rather straightforward. But we're going to generalize this proof, or you will generalize this proof when you start looking at representations of other semi-simple Lie algebras. So what we've done is we've taken some one-dimensional representations, and we've induced them up from a Borel to get these Verma modules, which are some infinite dimensional representations. And they're constructed so that they're highest weight modules. This vector v plus is actually a cyclic vector, right? All the other vectors you get by applying powers of f to v plus. And v plus is killed by e because, well, on v plus, e comes over the tensor, and we've said that e acts as 0 on this one-dimensional module we're inducing. So somehow this is sort of universal amongst highest weight modules for this weight lambda. So those are these Verma modules, and then generically these Verma modules turn out to be irreducible. They're infinite dimensional irreducible representations. But when you get lucky, when lambda is actually a natural number, the Verma module, which is infinite dimensional, turns out to have a finite dimensional irreducible quotient L of n. And those guys give all of the finite dimensional irreducibles up to isomorphism. So let's see if I can prove this. So suppose first that lambda is a complex number but not natural number, and take a non-zero vector v in the Verma module. So v is going to be some scalars times these f to the I v pluses. And if you choose the biggest I, so ci is non-zero, it's just a sum, right? So it's got finite support. and then you look at e to the IV, so let's see how to do that. So what you need to do this is you need to understand how does e act on f to the n plus 1 v plus, right? So if you're n plus 1 steps down from the top, how does e act? But the lemma that we just proved says that this is n plus 1 lambda minus n f to the n v plus. That's just that lemma, because in this case h acts on v plus as lambda. And you see this thing here, it's never 0 for any natural number n, because lambda is not a natural number. That's never 0. And so from this, it follows that e to the IV that I was considering before, right? So e is kind of trying to pull you back up again, and you never get 0 until you get to v plus, when of course ev plus is 0. But e of everything lower down, it raises it higher and higher. And so since I'm applying this maximal power of e, it'll kind of pop off all of these f to the j v pluses for j smaller than I, they'll pop off the top. And then this e to the IV, you'll get a non-zero multiple of v plus, which is a cyclic vector. Hence, v generates, and m of lambda is irreducible. But if that lambda is a natural number, then this f to the n plus 1 v plus is actually killed by e. So if it happened that lambda equals n, then actually now that equals 0, and this formula is exactly saying that e kills f to the n plus 1 v plus. So in fact, f to the n plus 1 v plus, f to the n plus 2 v plus, and so on, span a submodule of the Verma module in this case. And then you just look at weights. This is of weight so v plus was of weight n, and then we've subtracted those guys. So this is what, minus n minus 2. And in fact, it's rather easy to see that this is a copy of m of minus n minus 2, which we'd already shown is irreducible. The quotient of m of lambda by this submodule has basis just v plus, well, the image of v plus in the quotient fv plus all the way up to f to the n v plus. So it's of dimension n plus 1, and just do the arguments we've just made, and you easily see that that's irreducible. So that's this unique irreducible quotient of the Verma module. Okay, so we're almost done. We finally got to show that any finite-dimensional irreducible G module is isomorphic to one of these L of n's. Of course, the n will be uniquely determined by the dimension of the module you're looking at. So now take any finite-dimensional irreducible G module L. And as I explained above, you can find a non-zero highest weight vector of weight. Well, all we knew was that that weight was a complex number, right? So that's a vector so that HV is lambda V and EV is 0. So it follows that this space HOM over this Borel subalgebra B from C lambda to L is non-zero, there's a unique homomorphism sending 1 to V, because this is exactly saying that this vector V looks like the generating vector in that one-dimensional representation. But this is homomorphisms over B, or equivalently over the universal enveloping algebra. And so by adjointness of tensor and hom, it's the same as homomorphisms. I guess maybe I should have written the restriction there, then it might look more familiar. The restriction from U of G down to U of B here. This is adjointness of tensor and hom, or Frobenius reciprocity. And so this is so I've just put this tensor in, but of course this is our Verma module. So it shows that there's a non-zero homomorphism, a G module homomorphism, which is going to send V plus, that was 1 tensor 1, is going to go to the vector V that we picked there. And if V plus goes there, well then f to the I, V plus is going to go to f to the IV. Now hang on, L was irreducible, so cyclic, so this is onto. So L is a finite dimensional quotient of m of lambda. But we've worked out that the only finite dimensional quotients of m of lambda, they only happen if lambda is a natural number. And so lambda is n, a natural number. And this L, it must be isomorphic to the module L of n that I got before, where the dimension of L is n plus 1. And that completes the classification. Okay, so that's all looking great. So I'm going to prove one more theorem in the last 10 minutes today. So we've just classified all the finite dimensional irreducible representations. Now I want to prove that any finite dimensional representation of G is actually completely reducible. So having classified the irreducible ones, now I'm showing that actually any finite dimensional representation just is isomorphic to a direct sum of those L of n's that we just classified. So for the proof, it suffices, since we've just classified all the irreducible ones, to show that any finite dimensional one is completely reducible. All I have to do is show that there's no non-split extensions. This is sort of a fairly standard reduction. I'm not going to go through it. If you can show there are no non-split extensions between irreducibles, then it follows that every finite dimensional representation is completely reducible. And to do this, you just look at cases. So I mean, we're looking at x1, right? So we're looking at short exact sequences of this form. And we have to show that every short exact sequence of that form splits. So case 1 is the case when A is bigger than B. And so what we've got to do is we've got to think about how could H act on V. Now we totally understand how H acts on that irreducible L of A. It acts diagonalizably. And we knew the eigenvalues, right? There was A minus 2. All the eigenspaces were one-dimensional, all the way down to 2 minus A minus A. And similarly for L of B, they went B minus 2, all the way down to 2 minus B minus B. And so this V, it's an extension of these two finite-dimensional vector spaces as a G module. So certainly, as for the action of H, it'll have a submodule where H is acting diagonally with those eigenvalues, and it'll have a quotient module where H is acting diagonally with those eigenvalues. And if A is bigger than B, well then this A, it's the highest of any eigenvalue appearing either in the submodule or the quotient. So in this case, the generalized A eigenspace of H on V is going to be one-dimensional. Right, so generalized eigenspace, I'm talking about Jordan blocks, right? It's either going to be, because this generalized eigenspace is one-dimensional, it's just a one-by-one Jordan block when you think about this matrix for defining the action of H in a basis. And so all you have to do is in this L of A, we've got this highest weight vector V plus of weight A, and the A eigenspace in V is still one-dimensional. So if you just pick any eigenvector of eigenvalue A for the action of H in V, it's got to map onto some non-zero multiple of this V plus. So in other words, you can find a V in V of weight A mapping to V plus in L of A under this quotient. Why don't we name this quotient map pi? Then by the universal property, that adjointness argument that I just used, that's called the universal property of the Verma module, M of A, you get a G module homomorphism from the Verma module to V, sending its V plus to V. You see this E on V plus, E on V, because V is of weight A, E of V must be of weight A plus 2, but that weight space is just 0 in here because A was bigger than B. So that adjointness of tensor and Hom argument that I just used will give us this homomorphism. But actually, because V is finite dimensional, this must kill that infinite dimensional submodule of M of A. So it must actually just be giving us a homomorphism from L of A to V, and this gives the splitting. Of pi. And it gives you this G module homomorphism this way, and that composition sends V plus to V plus. So actually that composition must be the identity map because L of A is irreducible. Okay, so that constructs the splitting. In that case, it's quite straightforward. Case 2 is when A is less than B. Now, you could probably construct some dual argument to that, but since we have a duality on finite dimensional representations, you don't need to do that. What you have to just note is that x1g L of A, L of B is isomorphic to x1g L of B star, L of A star. If you dualize an extension, you get an extension of the duals, but the other way around. And L of A star, being as it's an irreducible representation of dimension A plus 1, is just L of A again, and L of B star is just L of B again. And in case 1, we just showed that x1 L of B, L of A is 0. So it follows that x1 L of A, L of B is 0. So we're done. And that leaves the hardest case when A equals B. And so now this is just a little bit more interesting, because here was our extension. So the highest weight is A, but the generalized A weight space, this generalized eigenspace, maybe I should use eigenspace, weight is always diagonal, for H acting on V is two-dimensional. And the argument that I gave above, in case 1, works fine if H is diagonalizable on this eigenspace. And you do just exactly what I did. You can pick an eigenvector lifting the vector v plus in L of A, and then use this universal property of the Verma module to construct the splitting. But we don't know this. Why not some Jordan block? So that's what it's all about. It's showing that actually H acts diagonally on this eigenspace. But now what I'm going to do is I'm going to take any V in this generalized eigenspace, and I'm going to note that EV is 0 because V is of this maximal eigenvalue, so EV would be adding 2. It would be in the generalized eigenspace for the eigenvalue A plus 2, and that's just 0 in here. And similarly, if you apply F, well, if you apply F to the power A plus 1, right, so remember that these, so we're going all the way from A down to minus A, all the way from A down to minus A. I've applied one more F than that, so I've kind of dropped off the bottom. So that generalized eigenspace isn't there either, so that's also 0. But in that case, e to the a plus 1, f to the a plus 1. So now I'm using the corollary. We haven't used it yet. Let's go back and remind ourselves. I'm using this exact corollary. I've got a vector killed by e, and I'm applying e to the a plus 1, f to the a plus 1 to it. And the corollary says a plus 1 factorial h minus 1, h minus a, v, by that corollary. But that's 0. And this shows that the minimal polynomial of h acting on this eigenspace divides the polynomial x minus 1, x minus a, right? So there it is. I've shown that when you evaluate that polynomial at h, that kills every vector in this generalized eigenspace. This is a product of distinct linear factors. Hence, by linear algebra, h is indeed diagonalizable. So that's the proof in that harder case, case 3. So we've now completely classified all finite dimensional representations of the Lie algebra SL2. It didn't take very long, but those are kind of quite profound applications of linear algebra in this subject.